So yesterday we found that, well, let me write that. Sorry. The momentum space version, sorry, the momentum space, yeah, the Fourier transform of the two-point function had this formula. But we also learned that it could, that it had to be written in this form. Where this means regular pieces as p squared goes to m squared. Okay. So this z happened to be this object. Where this was the zero momentum state, one particle. Okay. Now, so we know that if we take the coupling to zero, lambda to zero, we should get the free theory Green's function, or the free theory propagator. And the free theory propagator should be 1 over p squared minus m squared. Okay? So we shouldn't have this z here. Well, in the free theory case, let's look at what happens to this guy. So in the free theory limit, we have to compute this. But what is this? Well, this is just a regular vacuum of the free theory. This will be the free theory field evaluated at position 0, and this will be the state created by this operator. So when we evaluate this, what do we get? Well, you just plug this here. Now we don't get 0. So when you put this guy here, you commute, you perform the integral that appears here, and then you get the vacuum, which is normalized to be 1, then you get 1. So in the free theory limit, this object is just 1. Okay. Now in the interacting theory, there is no reason to expect there is 1. And people give a name to that. I think we said it yesterday. But so the physical interpretation is that it's a probability or is the amplitude for producing, for the field phi to produce a state of 0 momentum from the vacuum. Okay. In the free theory, that is exactly 1. In this case, doesn't have to be. But this z is called field strength renormalization. And the reason is that we would like to deal with a field that actually gives you an amplitude for producing from the vacuum the number 1. Okay? So it's more natural to rescale your fields so this is going to be called the field renormalized by a factor of z to the half. Okay? So that when you compute this quantity, you get 1. Okay? This is just for you to see this. So in this course, or for the remaining part of the course, we will just set z to be 1, and we will forget about it. Okay? All right. Very good. That's what we did yesterday. So we spent most of the time doing this. And then we learned our first lesson in renormalization. So there is a difference between, just a second, between renormalization and regularization. What do you think I mean when I say that we are regulating something? And what do you think I mean when I say that we are renormalizing something? So raise your hand if you, so, yep. Which of the two you want to tell me about?
Renormalizing is probably like adjusting for your viewpoint from different scales, energy or less scales.
Yeah, so it's adjusting parameters you had.
Yeah.
So which parameter we renormalized yesterday? Well, yesterday we didn't do lambda. We did the mass, the bare mass, right? We did the bare mass. And what do we mean when we say that we're going to regulate something? That's right. We had something that is infinite, and we regulate it, meaning we're going to find a way to make it finite, okay? Whatever way it works. So we make it finite. That means regulating your theory or regulating your objects. And after you do that, you can try and renormalize your theory, okay? Meaning try to find ways of defining physical quantities so that they don't depend on your regulator, okay? So yesterday we found our first example, which was of a renormalization. We said that we can renormalize the bare mass by imposing the condition that at p squared equals to m squared, the following must be true. This quantity should be 0, okay? And that gave a condition for m0 in terms of this. Okay. But today we want to switch gears and study something more physical. In fact, it was the way we started quantum field theory 0. We started with a physical approach. And we studied cross sections, right? So let me just remind you the setup. We said we have some beam of particles, okay? Particles of kind A. They are moving with some velocity. We have a bunch of particles B. They are coming here. Say that the relative velocity is V, okay? So if we have all these particles colliding, we will get some number of events of a certain kind. And then in field theory 0, we said that the number of events was equal. I mean, it's obvious that it has to be proportional to the total number of particles in the beam A, the total number of particles in the beam B. It has to be inversely proportional to the area of the beams, okay? Of course. And the constant of proportionality is called the cross section. So the cross section was something that has dimensions of area. And is the object that we want to compute, which is independent of the experiment you are performing, meaning of the setup, of the experimental setup, okay? An experiment performed at the LHC or an experiment performed at the Tevatron or any other accelerator that collides the same kind of particles and measures the number of events coming out. Once this is computed, this number is computed, it's going to be the same number, okay? So that is a physical object. It's a cross-section for some initial particles to produce some final particles, okay? Very good. We also said that sometimes you are not interested in something that doesn't, I mean, this thing has lots of information, but not as much information as we would like, because we have detectors that can actually measure the momentum distribution of the final particles, okay? So if you have detectors that not only give you a beep every time that they detect a particle, but they can actually tell you what the momentum of the particle was. You would like to define something more refined than this, right? Because from here, you can only predict the number of beeps that your detector will give you, okay? So we defined something more refined, which was the differential cross-section. And the differential cross-section was exactly the same object, except that now we want to find out the distribution of events, or how many events we get in a particular region of the phase space. So we had a shorthand notation for this. It was called the ellipse of the final states, okay? And we found that this quantity was proportional to the energy of the beams, of the original beams, times the relative velocity, or the speed, times an object that was precisely the physical object of relevance, the scattering amplitude, okay, the transition amplitude. Does anybody remember what this d-ellipse was? That's right, it contains, so the d-ellipse for the final particles was a tiny region in momentum space, or in the phase space of the particles, right, of the final possible particles. So that thing has to be a product of states, all possible states in the final particles that you want. So you want to restrict your attention to some particular outcome, okay? So you integrate over the momentum of those guys. But remember, we said that this was a little bit, that we were a little bit off if we think that this was the phase space. This was the wrong phase space, right? So what did we have to do? We had to correct it. With what? Yes, we had to correct it with momentum conservation. Not all these vectors would actually be okay. So if we sum over all the final states, we have to get the sum over all the original states, okay? In the initial states. Well, in this case, we only have two guys, so we can say PA plus PB. Okay. So we can say PA plus PB. Very good. And what else? Is this a complete phase space? We're getting closer. But can we have any momenta that add up to this PA plus PB are fine? Are those physical quantities? They have to be on shell, each one of them. And they have to go into the future. Okay? Yes?
If I'm not mistaken, we did this with T0 just for the one particle that you said, right? When we have the, well, we calculated everything for a term that you said that generically goes to 0, right?
No, that was in the second lecture. This was in the first lecture.
Okay, this is in general. I mean,
This is for the external. This is the phase space of some number of final particles going on. Okay. We're not doing anything special here. Now, what you're remembering is the following: that we then use unitarity to learn something about this object. Let's actually give, I think in my notes, I'm giving a name to these momenta, not to confuse them with these ones. So let's call these ones K1, K2 up to Kn, or some n final, okay? So we use unitarity to learn something about this object. What did we learn? From unitarity. We learn many things about this object, but one of the things that we learn from unitarity. What happens when you send PA plus PB squared? Imagine you're performing your experiment, right? And you tune your experiment so that PA plus PB squared happens to be very, very close to M squared. In other words, you are telling that the sum of the momenta of the two particles is almost becoming unshelled. That's right. So we learned that this guy, so let me draw it like this. So if we have A and B producing K1 up to Kn, we learned that from unitarity, we learn that as in the limit when PA plus PB squared goes to M squared, okay, this object had to factor, okay? So what we're going to do is called factorization. This is something we said last time. So what does it mean, factorization? Well, it has to go into something that looks like this, where you have A and B producing an intermediate particle, which we can call C. It's natural. But this object will diverge. It will have a pole located at, or something that looks like this. And the I epsilon, we even derived the I epsilon, if you remember. Okay? So we're very precise. And C going here and producing the final states. Okay? So we derived this formula. And from here, from unitarity, we learned that these amplitudes, they must all contain poles of this form with residues equal to the product of these two amplitudes. Okay? Any questions? No questions? Okay. So now, let's see what we can learn from here. Let's go back to our experiment. Let's now do some experiment.
Say that again about what the residues have to be?
The residue, yes. So the residue has to be, so what we learned, okay, what we learned is that M has poles of the form I over PA plus PB squared minus M squared plus I epsilon. I mean that the function has a pole. Of course, you can go very close to the pole and see how the function behaves, right? So when you go very close to a pole and you remove the singularity and see what is left is called the residue at that pole, right? Now the residue is nothing but, so let me write it here. The residue is nothing but the product of this times this. So what is it going to be? Is the product of this amplitude for A, B going to C times C going to the final states. Okay? So that's what we learned last time. And this was powerful enough so that at the end of the course, of the previous course, we actually learned a very powerful relation between Poincaré group and what else? What was the end point of the previous course? So we found a connection between, just assuming Poincaré invariance, we learned that, that's right, we discovered Lie algebras as the possible couplings of massless particles with helicities plus minus 1. Either they don't interact, or if they do interact among themselves, then the couplings have to satisfy the Jacobi identity. That's what we learned, okay? Now, let's do an experiment. Of course, any connection between what I'm going to say and reality is pure coincidence, okay? But still, it's an experiment we can perform. So let me actually get some, are these colored chocolates? So let's try to imagine how the experiment is actually done, okay? So we start with something here. I don't even know how to actually do it, but the way we produce the particle A is very often by colliding other particles, okay? So the way we produce electrons in an electron and positron collider is by scattering particles, okay? So there is something that is happening here, which we do by colliding some particles and producing this particle A. Of course, we do it billions of times, and then we produce a beam. But let's only look at one of these guys. So we do it, okay? Likewise, we're going to do it for our particle of type B. We produce this guy by colliding other things, okay? Now, doing this billions of times for all these guys produces the two beams that we have over there and that we're colliding, okay? But once again, we're following only one particle of type B and one particle of type A, which happen very conveniently to actually be two particles that will collide, okay? Most of the time, these guys just pass through each other and don't do anything. But these ones that I'm going to choose, because I get to choose, are the ones that will collide. So they come, they collide, and guess what? They produce, say, two particles coming out. Let me call them particles 1 and particle 2. Okay? Now, what do we have to do with those particles? I mean, your guess is as good as mine. I mean, I'm not an experimentalist, so I don't actually know. But for sure, something has to happen to these guys. We have to detect them, right? How do you think detection happens? They collide, right? They collide again into something, right? So they collide again. Well, say they collide into something that produces many photons. Okay. This guy comes here and produces many photons, and this might be something like a photomultiplier. Okay, same thing happens here. Okay. Now here is a proposal. Let's look at this picture, okay? Now, why couldn't we think about this picture as actually a scattering process where we took these guys as initial states, okay? And these guys as final states, okay? I mean, that's certainly the picture that I drew, right? Now, the only thing is that this experiment is done in such a way, this part is done in such a way that the sum of the momenta of these guys happens to be tuned so that we can produce a particle on shell coming out, okay? Same thing for this guy. And guess what? In this experiment, that's exactly what is happening too, okay? So now from this point of view, if we think about the total object, as a big, we remove the detectors from here, and we remove the production system, who knows what it is. From the whole thing, it looks like a big scattering amplitude, like this one. Okay? Many things coming in, many things coming out. But we know from unitarity that the scattering amplitude must have poles, okay? Poles of this form. Well, what are the poles that we are exploring here? Well, this big object should have poles of the form I over whatever the momentum of this particle is. Let's call it PA squared minus m squared plus I epsilon. This big object, of course, we don't write it as PA. I mean, in principle, it should be the sum of these momenta. But I'm too lazy to write the sum of all these momenta, and even more lazy to give it names to these guys. All we know is that before we take any limits, the big amplitude, okay, has a pole of the form, the sum of these momenta squared, and the sum of that momenta I'm calling PA squared minus m squared plus I epsilon. It also has a pole of this form, guess what? It also has a pole of this form. P1 squared. Let's actually use the notation that I decided to use over there and call it K, okay? And it also has a pole of the form K squared 2 times something else, times an object. But what is that object? What is the residue of that object? Well, the residue on all these poles, on all this set of poles, has to be the product of this, and this. But we're not interested in that, times this guy, which is the thing that we're interested in. This thing, if we now think about this like this, let's forget about where these guys were coming from. That thing is what we call the amplitude for PA, PB going to K1 and K2. As we get very, very close to the pole, right? In the limit, when these things are actually blowing up, the residue will pick up this contribution, just from unitarity. Is that clear?
We're still assuming that the second particles are on shell with the same mass.
Yeah. I mean, in actual experiments, these guys will all be different particles and so on. We're in our happy imaginary universe where there is a single scalar field and there is only one mass. Yes. So, sorry, we will have to fix that problem soon enough, but not now. Let's stick to our happy universe where there is a single scalar field with mass m, with physical mass m. Well, then this shouldn't be called a photomultiplier. It should be a scalar multiplier. But, okay, this is very important.
Can you remind us where we got how unitarity led to the poles?
That was a whole lecture. So I encourage you to go back and go through your notes and see how unitarity implied this thing. Okay? Very good. Yes?
What have we gained? Didn't we just write down originally that the thing we're interested in is the matrix, is the M?
That's absolutely true. So we have gained nothing and lost like 10 minutes. But we gained a very nice picture with colors and everything. Come on, dude. And there has to be some sense of. Okay. So I agree. So we should stop fooling around and let's go back to our 4-point Green's function. If you're upset that we have to stop having fun and so on, you know who to blame. Just reminded me that we have to get to something today. Okay? Yeah. Okay. So what is our function? We have G P1, P2, P3, and P4. This is the object that we computed. Actually, you guys computed it today. And all we do is to take Fourier transform. Okay. Very good. Now, just out of curiosity, we can also ask, what happens, right? This is a function that depends on momenta, right? We could now, just out of curiosity, ask what happens when we set the momenta, each of the momenta that we have here, to be very close to be on shell, okay? So what happens? When we take all the momenta to be very close to be on shell. Well, today you found that this correlation function, this four-point Green's function, seems to be blowing up. It blows up when this happens, right? Because we have these Feynman propagators all over the place, right? Well, indeed, that's true, and that's what you found today. So if you check in your notes from today's tutorial, you will see that all the terms actually blow up, but there are terms that blow up faster than others, meaning that they have more poles than the other terms. Yes?
It's just one M, right?
Yes. Sorry. Yeah, that's why you were puzzled, because it had to be only one M. Now, when we do this, okay, you probably realize that there are diagrams that contain actually 4 poles. Some diagrams contain only 2 poles, okay? So let's say that we keep all diagrams that have 4 poles, okay? Or we want to keep the leading order. By the way, I didn't assume, okay? Yeah. So let's keep all the guys that contain exactly 4 poles. That would be the leading contribution when we take this limit. So when we take this limit of all pi squares going to m squared of our 4-particle Green's function, what's going to happen is that we're only going to keep all the diagrams, okay, genetic diagrams, that contain one of these propagators. So let me actually denote this, or our 1-point Green's function here. Let me actually denote it by this. Okay? So this means this object. Okay? So today you found that there were diagrams that contain 4 of those guys, but it's clear that in the expansion of this Green's function, we're going to keep expanding and drawing diagrams, okay? And then we can imagine that we collect all diagrams that contain the sum of everything that produces a full propagator on this side, the sum of everything that produces a full propagator on this side, and so on. So there are diagrams that do that. Okay. Now, which diagrams did have the 4 different poles? Which ones?
The ones that were fully connected.
The ones that were fully connected. Did you all get that today in the tutorial? right? So the ones that contain all 4 poles are the ones that are fully connected. Okay? And there will be subleading ones. Okay? Now, in the limit, when this happens, well, this actually looks very much like the picture we have up there, right? So, why not make an identification? Perhaps the object that we have over there, enclosed in the blue circle, happens to be exactly the same as this object that we have in the blue circle. As usual, when I'm erasing and giving you time to think. Yes?
So the subleading orders, are they not physically observable?
Well, first of all, in this limit, they just don't contribute, right? And they cannot, they are not observable. But there are certain observables that can be computed from the correlation functions themselves, okay? So when you have strongly interacting theories, you can have, say, a quark gluon plasma, then there are certain quantities that are related to the correlation functions themselves. That's why we went through the trouble of computing the correlation functions, because they contain the observables of your theory. But if you happen to be only interested in scattering amplitudes, then somehow we overshoot it a little bit. Yes?
And that thing is the full propagator, right?
That thing is a full propagator, yes.
It contains all the series of one particle.
That's right, the one you computed this morning. Okay, so we have 2 choices. Either we can actually sit down and give a formal proof of this statement, or we can say that Lehman Szymanczyk and Zimmerman in 1955 actually did it for us. And that's why it's called, what we're going to write is called the LSZ formula, or reduction formula. Well, it's called a reduction formula because we're going to compute the transition elements, okay, that we need to compute cross sections from the Green's function by throwing away lots of things. So we went through a lot of trouble for to compute these Green's functions, and now we're going to throw away many, many things, okay? So maybe I shouldn't be saying this, but I just did. So cannot take it back. So that hints that perhaps there are other ways of computing S-matrix elements that avoid the whole computation of correlation functions from the beginning and then leading to stripping out or removing lots of information. But in any case, so what is the LSZ reduction formula? So can anyone tell me what do I have to do in order to extract this from the Green's function? I mean, in practice, what do we have to do? So here is this object, say, oh, by the way, we have a little technical problem, which I didn't mention, which somebody should have said, right? There is an important technical problem, actually. who is PA, who is PB, and who is K1 and who is K2, right? We have 2 incoming particles and 2 outgoing particles. Which of these guys is incoming and which guy is outgoing?
Does not matter.
Here, this guy couldn't care less, right? But in the computation we did, it was crucial to see which guys were incoming and which guys were outgoing. So what's going on?
But did we not invert? Like, could we not switch them from one to the other side and try?
Oh, you mean in the previous course?
Yes.
And how was that called?
Crossing symmetry.
Exactly, crossing symmetry. We said that that was something that experimentalists could check, right? There was crossing symmetry. And now we're seeing that if we compute things from the Green's function, we actually start with something that couldn't care less about who is P1, P2, P3, and P4 corresponding to that. But we have to find a connection. And what is the connection? Well, the connection is that some of these guys should have positive energies and some of them should have negative energies, right? Because otherwise, momentum conservation will not be satisfied. The zeroth component could not be 0 if all these guys had positive zeroth component, right? As simple as that. Momentum conservation tells you that P1, 0, the zeroth component has to be, if you add it up with this, with the zeroth component of this and the zeroth component of this, you have to get 0. So somebody has to be negative, right? So the guy that happens to be negative, we can take as the guys that are incoming, and the guys that are positive, we can take as the guys that are outgoing. But now we see from this formula that all you have to do is the same formula. So all you have to do is to take your p's and change what they are until you connect a formula where some of the guys are positive and negative to other formulas where the guys are positive and negatives. So what you're doing is an analytic continuation of this guy.
Sorry, can you repeat that last part?
Yes, that starting from here, we get a formula from which we can get any of the crossing partners of this guy by simply changing the sign of the zeroth component of this guy. So we can interpret them as incoming or outgoing, okay, by simply changing the sign. Now, what one has to prove, right, is that in the process where you take this guy, the P0 component, say, is positive. Now you take it to be negative. Maybe along the complex plane, no, doesn't matter. You want to go from the positive to the negative value, and you do it analytically, meaning that you think about the complex plane and you follow that guy. So somebody has to sit down and prove that there is no obstruction to doing that. You see what I mean? It could be that this function is so badly behaved that it has singularities all over the place. And when you try to move the guy from one side to the other, you will face a singularity in the complex plane, and you will be killed. And there will be no way to go from one side to the other. Okay? Now, do we know how to prove this? Well, I think the answer is no. To all orders in perturbation theory, we don't know how to prove that such a thing is true. But since we do it experimentally, we believe it's true, that we can actually analytically continue these things from one to the other side, okay? But in any case, to the orders where we can check and do calculations, you can actually see it from the computation that you can analytically continue, and there are no crazy singularities that will prevent you to go from one to the other, okay? So we can take some of these guys to be PA and PB, and some other guys to be K1 and K2, okay? Say we take, well, since we have PA and PB, we can take P1, so take, P1 to be PA, P2 to be PB, P3 to be minus K1, and P4 to be minus K2, okay? That's all I had to do to get that amplitude, okay? So when we do that, assuming that this is true, this times delta 4 of PA plus PB minus K1 minus K2 would be equal to the limit when PA squared goes to M squared, PB squared goes to M squared, K1 squared goes to M squared, and K2 squared goes to M squared. And guess what? We're going to compute the residue like you did in high school, not with a fancy contour integral like people would do in college, but just as you would do it in high school. And the way we do it in high school is by multiplying by the poles and taking the limit, okay? But we're gonna do it like that. And the reason, part of the reason is that this, in order to do it as a contour integral, it would be a contour integral in 4 complex dimensions rather than 1. There is a whole theory about how to do these things, but we're not gonna do it. So we're gonna use our high school trick. Oh, you didn't learn that in high school? Well, neither did I. Neither did I, but I'm assuming that nowadays they should teach the residue theory in high school. If they don't, then somebody has to fix that problem. Okay? Times our Green's function evaluated at PA, PB minus K1 minus K2. Okay? And that, my friends, is the LSZ reduction formula. So that's how we get the objects that we have to put into the cross sections from the objects you already know how to compute. Yes?
So,
did I miss something important?
So the right-hand side doesn't seem to denote P, PB, K1, K2 anymore.
The right-hand side.
Because I'm taking a limit.
Of P squared.
Oh, I see. Not P.
There is a lot of dependency.
Yeah.
Exactly the same dependence as here. We're assuming that the particles we're scattering are on shell. So the P squared of A has no chance to be anything else but M squared. That's right. Okay. So in principle, we're done, and we can all go home, but we should do an example. Well, which example? Well, it would be exactly the same one that you did in the tutorial. No, it's really a pity to do this. Let's do it here. Okay, straight. Well, by the way, you see how to generalize this, right? So if you have n states, what do you have to do? Yeah, so put n states in the final state, so n, say n here. Well, there would be n guys here. There would be n guys here. The same here. And guess what? Well, you have to sit down and compute a very complicated correlation function that has n plus 2 points. But in principle, there is nothing complicated. You just sit down. I mean, it's, what is it called? Yeah, it's just long. It's not complicated, okay? People have a terminology for things like that.
We'll be calculating 2-point functions, 4-point functions, what about 3-point functions? We saw that they could.
In our theory, they vanish, yes.
So, I mean, then I will never have a process from 2 particles generating 3.
No, not in our not in our happy universe. Yeah. Okay, so let's do the thing that you all guys did today. Okay, so the Feynman diagrams are this guy, this guy plus this guy plus this one plus tons of other diagrams plus this diagram plus this diagram plus this one. No, please. Plus this diagram plus tons of other things. Okay. Now, well, these guys ended up giving us propagators, okay? But only these two propagators we get. Here we get two propagators as well. Here we get these two propagators. So what happens when we multiply by the 4 propagators and we take the limit? What happens to this guy? It's gone. Okay, so now let's take the limit. So let's actually compute. Okay, so this guy doesn't contribute. Very nice. This guy doesn't contribute. This guy we don't have to worry about. Neither this guy. All these guys are boring. So the first one that contributes would actually be this one. Okay? And as we all know, there must be an overall momentum conservation for everything that we do. And so what's the contribution of this diagram? Well, this diagram has the 4 propagators, right? You computed this morning. Has the 4 propagators, has the coupling constants minus I to the minus I lambda. So let's actually do it here. This guy, this diagram is minus I lambda times the 4 propagators. Is that what you got? Now we multiply by the 4 propagators, take the limit, and what do we get? Yeah, we get minus I lambda. Very good. We worked so hard to get that lambda over there. That's great. Yes. Very good. Now, are there any other contributions to order lambda? No? So we are done. We computed the cross-section, or we can compute the cross-section of this theory to order lambda, okay? Or that's what we have done, basically. Now, let's keep going. Let's compute this guy. So what do you think this guy gives? Well, again, it has the 4 propagators, but we're multiplying by the 4 propagators, so that's gone, okay? We have the symmetry factor, which Tibra reminded us yesterday, that is a half for this diagram. And now we have to give names. Let's call this L, okay? And hopefully I'm not going to get it wrong today. So say we have PA, PB, K1, K2, okay? So 1, so we have this. We have minus I lambda squared because we have 2 vertices. And we have to integrate D for L, okay? We have 1 propagator. So we have an I squared because we have 2 propagators here. So, and then we have L squared minus M squared plus I epsilon. And the other propagator, that's a tricky one that I'm going to get wrong, unless, okay, so let's try. So this guy will have to be, say I define it going in this direction. So what's this momentum? So it would be L minus PA minus PB, right? I hope. So we get L minus PA minus PB squared minus M squared plus I epsilon, plus 2 other contributions. which are this guy and this guy, so those are very similar. And then we're down to order lambda square. So this is great. So, of course, there is always a little dark cloud in the formula. What do you think it is? Yes, that this integral doesn't exist. This integral is infinite. But still, to order lambda, we can be happy, right? So let's actually conclude this part by saying, well, to order lambda, m is minus I lambda, and therefore, our differential cross-section for AB going to 1, 2 is equal to lambda square 4 times EA, EB, B, and the d libs of particles K1 and K2. Okay? Now, here is an exercise in quotation marks for anybody who wants to do it. Integrate this. So just put the integral sign here and put the integrals that are missing on this side with the definition that I gave you. Carry out these integrations, okay, and show that the total cross-section, so this is called the total cross-section for obvious reasons, is lambda square. Of course, you will have to work out the factors of 2 pi, but I'll be happy if you just get this with this, okay? And that's our first full cross-section that we can compute, or that we have computed. Thank you. Yes, it's the energy in the center of mass, or the center of mass energy. Also known, E squared is also known as S, or also known as PA plus PB squared. Okay? Remember S, T, and U? Okay. If you don't, that's exactly what I was about to remind you. Oh. So let me just remind you of the Mandelstam variables. So for 4 particles, meaning 2 going to 2, this is the process we're studying, people like to introduce these variables well, let me actually do it in terms of 1, 2, 3, and 4, and then you can translate into A, B, K1, and K2 using this, okay? It's going to be tricky for you to do it because this is going to be up while I do it here. But you have it in your notes. So I'm going to define this as P1 plus P2, okay? T is going to be P1 plus P4, and U is going to be P1 plus P3 squared, okay? Now, why did I bother to write this? Well, I'll tell you in a second, but they satisfy this condition. The reason I bothered to write this is that our M, our amplitude, PA plus PB going to K1, K2, whatever it is, it can only be a function of S, T, and U. Of course, they are subject to this condition, and our coupling lambda and the mass of the particle, okay? Now here, we can finally conclude the whole process of renormalization of this theory, okay? Of course, I told you that first we should regulate the theory. So we should find a way of regulating this integral. But after we regulate it, we have to do a renormalization. So how do we do the renormalization in this case? Well, it's not very difficult. We just take this guy and say, oops, we didn't really know what this guy was. Okay? So let's call it lambda 0. So this guy seems to depend on all these parameters. M, we already know what it is, okay? So we already fixed M. Now, how would you define the coupling of the theory or the strength of the interaction? Well, you can actually do an experiment, make an experiment and measure something, right? So here is the final step in the renormalization, which is the following. We're going to define okay? Of course, at this point, this is 4m squared, okay? Whatever function we get of lambda 0, however complicated it is, this object is going to be minus I lambda, the physical one. Okay? And we're not going to prove it in this course, but this renormalization condition, together with the mass renormalization condition we found yesterday, is enough to make the theory well-defined. Okay? Very good. All right. Now, we have to be brave and go back and deal with the problem, right? With this integral.
For the first order in lambda, that m was just minus I lambda.
Yeah.
And so we're going to say that that's lambda 0 now, right? But
well, at this point,
yeah.
At this point, we're going to declare that that object is a physical coupling, right?
So
This object. Right? This is the normalization condition. After you impose this, then you have to express everything as a function of this lambda. And to leading order in this lambda, lambda 0 and lambda coincide. Then the cross-section would actually be the physical lambda. To leading order. Right? To leading order, the two numbers coincide. Of course, the next order is an infinity, but that's why we're going to do something about it. Yes.
Those are the s equals to t equals to 0 and u equals to 0. Are those physically realizable?
So is this in the physical region? That's the question.
And sometimes.
Well, that's a good question. Let's think about it.
But if it wasn't, then we could have chosen another.
Yes, that's right. Yeah. Okay. So what do we do with these infinities? Well, basically the answer is whatever you can. And let's mention some of the things that people have done. So we have a cutoff. Okay. So you just try to carry out the integration, up to some scale lambda. Why is this not very satisfying? What symmetries that we think are very, very important are obscure when we use this regulator? These are called regulators again, right? So if we do this, what symmetry that we know and love becomes obscure? Lorentz, right? Because clearly, if you perform a boost, this thing will also be changed, and then your formulas will seem to be changed. Right? Now, you could just do it and see whether, when you are done calculating a physical object, the answer is independent of this cutoff. Okay? If you do, then you're in luck, and you say, well, you declare that answer to be your final answer. But sometimes you are not as lucky. Sometimes, when you impose a cutoff like this, there are some symmetries of your theory that will not survive this cutoff. Okay? Then what do you do in such situation? Well, maybe you have two options. You say, well, maybe that symmetry of my classical theory is really not a symmetry of my quantum theory. Or you could say, maybe my regulator is actually a bad regulator for some reason. Okay? So the only way to tell would be to find another regulator. Okay? So there is another regulator invented by Pauli and Villars, which we're not going to discuss, but once again, you should learn about it. And there is one that was invented by Etfour and Bellman in 1972. And we're going to say what it is, okay? So let's look at our integral. Let's think about this regulator in the example of our integral. So our integral is integral d for L. I don't know. Don't ask me. There you go. Okay. Yes. Okay, so how do we do this integral? Well, it looks incredibly complicated. In fact, imagine it's an integral, it's a 4-dimensional integral. If this was the full answer, if this was all we had, it wouldn't be that bad, right? Because we can go to polar coordinates and do the calculation. But on top of that, we have this guy, and we have these guys here that mix with this, okay? So it looks very, very complicated. In fact, people suffered a lot to carry out things like this, never mind that they are infinity. But Feynman, once again, came to the rescue and made a very simple observation. And introduced something that is now known as Feynman parameters. And the basic observation he made was that the following identity could be useful. If you have any two numbers, A and B, okay, you can write this as the following integral. And if you don't believe me, you put it in Mathematica, and Mathematica gives you this immediately. Yes?
People claim that Schwinger invented it, but Feynman got the credit for it.
Okay, so let's call it the Schwinger-Feynman parameters. In any case, it's a nice trick. So what do you think I'm going to do with this? How am I going to use it on this formula? What is going to be A and what is going to be B? I mean, it's unfortunate that I call the particles A and B. This could be anything. This could be C and D, and then C and D. In fact, what we're doing now is something that you should do even if you're using a cutoff regulator. So we still haven't done anything to regulate the integral. So any ideas? Who's going to be A? And who's going to be B? That's right. So let's think about this as A. And this guy is going to be B. And if we do, what do we find? We find that our integral, let's call it I, is equal to integral d for L, and then we have integral from 0 to 1 dx of 1 over x L squared minus m squared. Let's forget about the I epsilon. Okay, it's not going to do anything special. L minus PA minus PB. Let's actually expand this. Okay, we're going to expand. So we're going to get L squared minus 2 times L dot PA plus PB plus S, okay, which we define over here, minus M squared, all that squared, okay? Now there is something nice about this formula. If you see, the leading order is L squared, because we have this with this. The x cancels, and we get this, minus something that looks like a vector. Let's call it, I don't know, maybe we can call it capital K, that depends on x dot L, plus something else, which we can call, say, a problem with m of x. Okay, so the object has this form. Okay. Now we can shift M so that this thing becomes L squared minus some quantity, which I'm going to call delta squared, that depends on x. Okay? So shift L so that this happens. Now our integral becomes integral d for L, integral from 0 to 1 dx of 1 over L squared minus delta of x squared. Okay, so here is where you have two options. One is to introduce a cutoff. Now the integral is finite, and then you can swap the integrals and carry out the integration and get an answer, okay? So that would be the cutoff procedure. What we're gonna do is actually something at first looks much more dramatic. So what we're going to do, the first step is we're going to take L0, okay, and think about L0 as an integral over the complex plane. The contour clearly is the integral over the real part. And what we're going to do is to shift the contour in such a way that the contour is now over the imaginary axis. Okay? This is called a weak rotation. If you don't like it, then you can simply get away and say, I'm gonna make a change of variables. And I take L0 to be I L0E. That's the low budget version of the, of the weak rotation. This is a change of variables. No problem. I just do it. Okay. E, very good. Yes. You know that people, when they didn't like Lorentz transformations, they didn't like space-time and all that. So they, in the very old times, they introduced an I and thought that, no, the thing is that everything is Euclidean, but the time is imaginary, right? So this E stands for Euclidean. In fact, when we do the rotation now, everything becomes Euclidean, literally, right? So this L squared, what does it become? It actually becomes the norm of the object. Yes?
This is problematic even if I use this trick, right? So what you're going to do is...
What do you mean is...
I mean, this integral that I have here,
yes,
is still divergent, right?
Yes. I'm not doing anything still with the divergence. Yeah.
All right.
Yes. I mean, we're just rewriting the object, and I haven't done anything illegal because I haven't swapped the integration radius, right?
What if you swap it?
We're going to do it,
okay.
but don't you worry.
Not be legitimate to swap the...
Well, because you have to. That's only true when both integrals converge, right? Think about the integrals. Remember that integrals are defined as a limit procedure, right? If you have two integrals, you have two limits that you're taking. And you are allowed to swap them only if the two limits actually exist. Well, not even there. You have to be careful, right? Sorry? L0 is the zeroth component of this vector. Okay, sorry. Oh, actually, this would have been much better because then we can put the E here. I knew there was something funny with that. Very good. So if we do that, then our R squared, which was L0 squared minus L squared, becomes minus L Euclidean squared, where Euclidean means literally an integration over a four-dimensional Euclidean space, okay? So if we do that, our integral now becomes an integral d4 L Euclidean, integral from 0 to 1, dx, 1 over L Euclidean squared plus delta squared of x squared, okay? Here is where the inspiration comes.
You also get an I.
Yes. Up to factors of I and 2 pi's and all that, yes. Yes. Okay. Now comes the inspiration part. You say, well, why, I mean, we live in 4 dimensions, or so we believe, right? So, but in general, I mean, we could think about a field theory that lives in d dimensions, okay? So why not try and do this integral in d dimensions, just out of curiosity, and see what the integral would look like in d dimensions, okay? So let's replace 4 by d, just out of curiosity. So we get an integral dl 0, 1 dx clearly, there are dimensions where this integral converges, okay? So let's assume that we're working in one of those dimensions, so we can swap the two integrals. You knew I was going to get there, right?
Okay, one thing. If we're going to do this calculation in a higher dimension, shouldn't we calculate, for example, the
Oh, no. In higher dimension, it would be
or
terrible.
a different dimension where
Yes.
that this thing converges? Should
Yes.
we do that from the first step, which is calculating the propagation? Because we calculated it in a four-dimensional space, right?
No, but you can check that the propagator, this form of the propagator is true even in any dimension. Yes.
Okay.
What is different is that this LS square will have many more components or less components, right? When you calculate it, the momentum L will have more or less components, okay? Now, we happily switch this thing. Oh, sorry. D. And then we have LE squared plus delta squared. Now this is an integral that literally anybody in high school can. I mean, some people in high school, I didn't, but some people learn how to integrate in high school. Right? Yes. Oh, now maybe not in high school. Okay. So this is something that can be done. Okay. Is D an integer? D is, I haven't told you what D is, right? So, but we can actually do this integration. So in fact, this is something that can be done, okay? And people have done. But I'm not going to do it, okay? So you can do this. Do this integration. You see, the only difficult part of the integration is really the angular part. You have to compute the volume of a sphere in d dimensions, right? Because now this is all Euclidean. So this thing is actually the length. So you can actually think about this LE square as being r squared, okay? It's a radial direction. You can go to polar coordinates and literally do the integral over r, and that's no problem. Then you have to find a way to compute the integral of a sphere in d dimensions. But that is also easy to compute. You just do it, okay? Integrate over all the angular variables one by one, and you get a formula, okay? Once you have the formula depends on d, okay? Now, once you have the formula, you can do whatever you want with d, okay? So once you get the formula, so this integral will be an integral from 0 to 1 dx of something. So let's call it, I don't know how we can call it. We can call it r of d and x, okay? So once you get it as a function of d, you can now do whatever you want with this formula, right? It doesn't remember that it came from a computation where you had to do it one by one dimension at a time, because you are doing the angular integrations on the sphere, right? So it doesn't remember that it came from there, and then why not take b to be 4 minus a very small parameter. I mean, after all, we want to think about 4 dimensions. Okay? And we know that the integral diverges in 4 dimensions. But if we go lower in dimensions, then hopefully the integral converges and makes sense. Okay?
When you take it out, what's the need for having a 4 minus epsilon?
Oh, because now our formula depends on d. And nobody,
Will
no.
it still diverge if you just put 4 in there?
Yes, sadly, yes. Yes, so if you just put d equals to 4, you get infinity. So you say, well, let's not put 4, let's put 4 minus epsilon, and then expanding epsilon, okay? So you put this, you evaluate this in 4 minus epsilon, then you do a Lorentz expansion, right?
Live in slight
slightly less than 45?
Sorry?
So we live in slightly less than 45?
No, epsilon is actually positive. So 11 is very different, right? From what I'm doing.
Yeah, so we live in slightly less than 45.
Oh, sorry. Yes, sorry. I understood 11. So for obvious reasons, right? But
Don't you have to sometimes regularize with epsilon less than 0? So we live in both slightly less than.
no, epsilon less than 0. Epsilon less than 0 is important in order to regularize infrared divergences.
Yeah, so
but infrared divergences are something that have a very physical origin, and it has to do with the fact that if you have massless particles, okay, then any particle that you have that you think is a single particle with a given momentum, there is no way to distinguish it from that particle and particles that come in, and that particle emitting lots of small momentum particles, right? So the probability of computing anything, of getting an amplitude where you produce a given set of particles with a very definite momentum at the end actually vanishes, okay? Then you have to sum over all these guys to get something finite. So the infrared divergences are very physical. They have a purpose in life. You deal with them first, and once you deal with them, they cancel out very nicely. There is a whole chapter about that, which I encourage you to read. It's very amusing. Chapter 13 of Weinberg. Okay? So, yeah, I'm getting sidetracked, but it's so spectacular that you should really read it. Chapter 13. And then once you get rid of the infrared divergences, you worry about your UV divergences, okay? Now, you expand this. Of course, our theory, in our happy universe, there are no infrared divergences, right? Because we have a mass. There are no massless particles. So our theory doesn't have infrared divergences. It only has UV divergences. And when you expand this, guess what you get? You get 1 over epsilon plus other terms. So there is your answer. To what happens if you put d equals to 4? You have to set epsilon to 0. You get a pole. Okay? This procedure of getting regulated objects is called dimensional regularization, for obvious reasons. Or people call it dim reg. So you will hear people talking about this all the time. Yes?
I guess it is something when we're doing the calculation of the integral on L, we're integrating over whole space-time.
Which integral? Over L? Yeah, this is d for L.
Right. So if I do that, then when I'm doing any dimension, and I do this in spherical coordinates, then that integral only converges for a particular dimension, is because I'm integrating between 0 and infinity, right?
Yeah. The integral over R is done from 0 to infinity. Yes.
So I don't know. I think there's a problem. I mean, that integral will still diverge.
Well, I said I'm going to assume that d is in the region where this integral converges, right? So you just do it. Yes.
So the ellipses, is that finite? The one.
Yes.
That's
So
finite.
these are higher orders.
But finite.
Well, higher than 1 over epsilon. The next one is order epsilon to the 0, right? Yeah, so maybe I should say that. That's actually right. Plus, so you will, the next thing would be order epsilon to the 0. The next thing would be order epsilon and higher orders in epsilon. Okay? Very good. So just, yes?
So just to make sure, was the whole point of this just to see how this thing blows up? Is that the idea?
Well, you see, very good. That's a very good question. So we do this. We get our 1 over epsilon answer. Looks terrible, but it's, as long as epsilon is greater than 0, it's just a number, plus other terms here. We plug it into our formula over there, right? So we now have our formula over there. We plug it here, and guess what? Well, we have a 1 over epsilon plus other things for each one of these 3 diagrams, but nobody said what lambda 0 was, right? So we have to solve the equation that I told you. We set S to be 4 times m squared, t equals to 0, u equals to 0, and we now impose that this formula equals minus I lambda, and then lambda 0 will depend on epsilon, necessarily, right? Now, the little miracle is that after you do this, and you decide to compute more complicated processes where 2 particles go to 4, say, right? You don't have to invent anything new. What you did with this regularization procedure, with the first regularization and then renormalization procedures, are completely enough to deal with any divergences that you encounter in the perturbation expansion of any amplitude that you calculate for this theory, okay? But that is a whole subject by itself, okay? So in this course, we're going to stop here, and this is the last time we talk about renormalization, and maybe not regularization, but about renormalization. This will be the end in this course. So you will have to wait until you go to QFT2, okay? Very good.